Another vector operation that we need to understand is the vector cross product. The vector cross product is another vector operation. In this case, you input two vectors again, and you output a vector this time. So it's similar to the dot product in that you are relating two vectors, but in this case, you are getting a vector outcome rather than a scalar outcome like the dot product gave us. More specifically, this vector operation is producing a vector that is perpendicular to the plane containing both input vectors. So this output vector is perpendicular to both input vectors. And the magnitude of this output vector is a measure of how perpendicular the two input vectors are. If they are perfectly perpendicular, you get the maximum output. If the two vectors are parallel or anti-parallel, you get 0. And the magnitude of the cross product gets bigger as the vectors get more perpendicular. So we use the vector cross product for various reasons. One is to find the normal direction or the perpendicular direction to a vector or to a plane. There are a couple equations for a vector cross product. The first one, if we're saying the vector cross product here, notice I have the double absolute value bar. So this is finding the absolute value, the magnitude of our vector cross product. And the magnitude of our vector cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between those two vectors. So again, it would be the magnitude of vector A times the magnitude of vector B times the sine of the angle of B minus the angle of A. And notice here that these two directions are in standard form. We were able to be a little bit more relaxed about the direction when we talked about a dot product because the cosine is a even function, and it didn't matter if this value was positive or negative, but a sine is an odd function, and it's important that we distinguish the order of these two terms. It would be the angle of vector B in standard form minus the angle of vector A. This is also assuming that these two vectors are in 2 dimensions, that they are in standard form in the xy plane. Another equation for the vector cross product is thus: it is a combination of all of the different components of the 3 vectors. So if you have them in in component form, you can multiply all those together. The way where this comes from some linear algebra and some matrices. This is the best method to use when you have vectors in 3 dimensions. What you want to do is have a matrix, a 3x3 matrix here. You put your 3 unit vectors in the first row. When you have vector A cross with vector B, the order matters. So we're going to put vector A first. We're going to have the 3 components of vector A, and then vector B comes second. So the 3 components of vector B go underneath it. So again, you have to have a 3x3 matrix. You have to draw the vertical lines on either side. That's one of the rules of dealing with matrices. The top row are your unit vectors. The middle row are your x, y, and z components of the first vector. Your third row are the x, y, and z components of the second vector. Then you're going to take the first 2 rows and rewrite them just outside the matrix as you see here. And so what is happening there is we are able to find the cross product. When we're going down and to the right, we are getting our positive terms. And when we're going down and to the left, we're getting our negative terms. And if you compare these terms that we have here to these terms that we have there, you will see that these two are equivalent to one another. So this would be difficult to memorize, but this process is one that you'll be able to remember and be able to execute. This is the easiest way to do it, particularly when we have vectors in 3 dimensions and you have a lot of non-zero components here. The third method is basically to use the FOIL method term by term. We said that the vector cross product is largest when the vectors are perpendicular to one another, and it's 0 when they are parallel to one another. So I hat crossed with j hat would give us k hat. Because I hat and j hat are in the xy plane, the output vector would be perpendicular to the xy plane, and so perpendicular to the xy plane would be the z direction. We can also say that j hat cross k hat should give us I hat. this would be the YZ plane. What's perpendicular to the YZ plane? The x-axis is perpendicular to the YZ plane. So our unit vectors are all perpendicular to one another. Our unit vectors all have magnitudes of 1, so that's not changing anything there. And so what we can say here is I hat cross j hat is k hat, j hat cross k hat is I hat, k hat cross I hat is j hat. We're going counterclockwise, which is our positive direction. If we reverse that, j cross I is negative k, I cross k is negative j, and so forth. And so if you have a vector with just a few terms, if you have one vector that is being crossed with another vector, you can FOIL these terms out, and the cross product works similar to regular multiplication. So in this case, 2 times 3 would give us 6, I hat cross I hat, and then 2 times 4 would give us 8, and then we still have to do the vectors I hat cross with k hat. And so I hat crossed with I hat is 0 because those I hat and I hat are parallel to one another. And so the cross product is 0. If I use my little picture over here, I hat crossed with k hat would be j hat, but I'm going clockwise, which is my negative direction. So in fact, I hat crossed with k hat is negative j hat. And so putting all this together, I get negative 8 j hat. This was pretty straightforward for me to do because there were just a few non-zero terms to consider. If I have a lot of non-zero terms, this is going to be the faster method for me. And then to finish up the vector cross product, a few general rules that we have is that the vector cross product is an anti-symmetric function. Anti-symmetric means that it's symmetric, you can reverse the order, but the anti means that when you reverse the order, you get a negative. Because what's happening is A cross B is giving us a vector that is perpendicular to the plane that is that includes vectors A and B. It's perpendicular to both vector A and vector B. B cross A is also perpendicular to both A and B, but these are in opposite directions, and the negative sign reverses the direction of that vector. The cross product for parallel vectors gives us a null vector, gives us 0, and we can find this direction. We can find the direction of a vector using the right-hand rule. For the right-hand rule, you take your right hand, you hold your palm flat, and you stick your fingers. Hold your wrist, so that your fingers point in the direction of vector A. And then you have to twist your wrist so that when you curl your fingers into a fist, those fingers curl into the direction of vector B. So in this case here, your hand is going sort of like this in the direction of vector A. When you curl your fingers are curling this way, which is curling into the direction of vector B. Then your thumb points in the direction of your cross product. Your thumb points straight up, which would be in the direction of A cross B. So the right-hand rule is one method that you can use to estimate the direction of the cross product, and then you can use one of the equations above to find the components or find the magnitude.